She was gonna.
Please don't make me do paperwork. Oh my God. We have 4 days till spring break, and my back is screaming. We can do this. Just keep the inside thoughts inside.
She's gonna beat you guys in bed wars.
Oh.
To be fair, esports is done for the season, and I know nothing about the Minecraft game, so.
Did you guys win anything?
We qualified for playoffs, and we did win several matches. We did not make it to state finals, but that's okay.
Next year.
We do, because Rocket League, we did not play in varsity because we didn't have enough people that would show up regularly to play it. All right. Let's take a look at this. So we've got a couple new words up here. We've got scalars and vectors. We have probably heard the word vector before because, you know, this guy is Vector. He was committing crimes that have both magnitude and direction. That was his little phrase. Magnitude and direction is what a vector has. What our magnitude is it relates to like distance. What vectors look like, and we'll get into this more just to think about it, it's kind of like a ray. It'll have a direction and a magnitude really talks about like the length, the speed, how fast it's going. So vectors look very much like rays. We'll get into that as we get further into talking about vectors. We're not going to be doing like much graphing with them, but just to give an image. No, we're going to do like a quick sketch and like talk about what it means, but like we're not plotting or anything like that. So where we see vectors most like real world, easy access, something we'll have a vector in, is if you ever look at the weather maps where they have the wind map and it has like what looks like the grid of like little lines that says that the wind is doing this. Like these kind of things, those graphs, they'll pull them up on the weather stuff. Those are all vectors. They're all measuring wind speed, direction, and magnitude. Okay, so that's where we see vectors. I think most people see them most frequently, or in, you know, Despicable Me. Okay, so what a scalar is, it's kind of like the coefficient of a vector. It is part of it. It is speed, it is mass, it is energy, it is distance, something like that. It's not really changing. Vectors are all about magnitude, so it's going to have that length, force, speed, whatever, and a direction. So it's moving east, it's moving north, it is dropping, it is lowering. I'm going to give you some examples and we'll talk about scalars versus vectors in like word examples. But scalars are basically coefficients. It's a thing. And our vectors include a direction. So it has to include a direction. Okay, so I'm going to give us a few examples. You don't necessarily need to write them all down, but if there's a few that help you kind of visualize clearest, you might want to write them down. But I'm going to put up several examples. We're going to talk through them. Like I'm not going to write really much other than these words. Okay, so thinking about scalars versus vectors. A car that is driving 75 miles an hour. Ow, that went up to my wrist. Yeah, the static shocks are strong. I could feel that one all the way up to here. All right, so if we have a car that's driving 75 miles an hour, we have a speed. Definitely a speed. But we do not have a direction. So a car going 75 miles an hour is a scalar. This would be a scalar value. This is a scalar. And then if you walk 4 miles an hour towards the store, so we're going to the store, meaning I have a speed and I have a direction. It's not a super specific direction, but it is a direction. So since we have both a speed and a direction, we're going towards the store, this one's a vector. Vectors need to have both our direction and our magnitude. Magnitude would be counting as speed, strength, how quickly it's changing. So if we have the box in the west corner has a mass of 12 kilograms. What do we think about that one? Why? It's not a direction, it's just sitting in that corner yonder over there. So this one is just a scalar. You push a box with a force of 10 newtons. Scalar. We don't have a direction on this one. I've got the weight of the box, I've got a force, but this is a scalar. You push the 12 kilogram box with a force of 10 newtons going east. That's a vector. Now that I have this direction, this is a vector. It needs to have a direction and a magnitude. So you can think of it like a scalar. It's very similar. So if it has both a direction and a magnitude, then it's a vector. Magnitude would be like, I think of it like distance. Like that 10 newtons, that would be our magnitude. East would be our direction. So that would be the strength. So the magnitude of an earthquake measures its strength. So the magnitude of a vector is how strong it's going. So this is 10 newtons versus if I did it with 2 newtons. So I'm pushing it harder. So this would be my magnitude direction. We're going to talk about magnitude a bunch later. Tomorrow. We're going to talk magnitude specifically tomorrow. What about for the time is 12:30? Does this say scalar at best? I would say it doesn't have to be either one. I would totally take neither on this one because I know I heard somebody say that. But this is definitely not a vector. So I'm absolutely okay with scalar. I would also be okay with neither on that one because that's not real. There's not really much going on there. It's just a thing. Okay, so it needs to have both a direction and a magnitude. Okay, so I'm going to show you a bit more about vectors. So it looks like a ray. If we're going to do about any graphing, they look like rays. And we are always going to think of vectors being at the origin because they are very, very equivalent. Location does not matter on a vector. Location does not matter. As long as our pieces are all moved in the same way, as long as our direction and our magnitude are preserved, these three vectors right here, they're all three, my light blue, my pink, and my purple, they count as the same vector because their starting point and their ending point, their direction and their magnitude are the same. We call the initial point the one that's at the origin. So it would be the one that doesn't have an arrow. And the one where we put our little arrow is called the terminal point. When our initial point is at that origin, that's called standard position. And then the magnitude of the vector is the distance. It's the length of the little segment we draw. So our magnitude is the distance. We typically set them up at the origin. Bless you. So this is our initial point. This is our terminal point. And the that's not what I meant. I'm going to pen. The distance, if we were to measure that, this distance is our magnitude. So it's all about that distance. So again, you don't need to write every single word up here. I was just trying to, put things in it because these are weird. That is how vectors look when they're graphed. Like they will just be a little ray on a thing. You don't, no. It's like we will draw some just so that we can see visuals on things. But like it's not going to be your graph is wrong kind of deal. Okay, so we're going to, all of this section is vectors. So we're going to be in vectors for a hot minute for the rest of chapter 8 has vectors in it. So we gonna go pretty in depth on the vectors. They after spring break, April 16th, I want to say it's the 16th. Okay, so these, they don't come up in like calculus as much. I don't think I really had vectors happen again until I got into grad school, but like they come back up every now and then.
It is trigonometry, but you're looking at the speed of the triangle.
I was gonna say, we'll get to where it relates to trig in just a little bit, in a little bit. Okay. So a lot of times when we get the direction on a vector, we're going to get a bearing. We can get a quadrant bearing like we've been doing, our north, 32 east, those guys, where it's based off of our never eat soggy waffles, that kind of stuff. Why is it not letting me? Oh, yay, it's frozen. Tried to erase that little line and it froze on me. Come on, come on, come on. Ooh, it froze hard. Let's try that again. There we go. Aha, got it. All right, so like our bearings, quadrant bearings, that would be our never eat soggy waffles. And our north 32 east goes from the north towards the east at a 32-degree angle. So like that would be north 32 east, just as a quick reminder on our bearings. And then there's also something called a heading. You hear that a lot in pirate movies. Where's my heading? Jack Sparrow says it a lot. We have a heading. That kind of stuff. And what that is that's just a bearing, but only from north. So it only goes north and east, and so it's just going to have bigger angles. So a heading of 60 degrees would be north 60 east. So our heading of 60 would be here-ish. A heading of 200, we would go around past our 180 and then 20 degrees this way. So this would be our heading of 200, which is actually south 20 degrees to the west. Because the quadrant bearings deal with these little angles off of the south-west guys. And the 200 is based off of north and east. So it's north 200 east or south 20 west, because north 200 east is weird. So heading is based off of north. Quadrant bearings give you the details. Let's see what's next page. Okay. So there's our heading and our bearing stuff, because those are all going to come into play on this stuff. We're going to start being able to work with stuff here just on this next one. You could do them in radians. Typically, bearings and headings are done in degrees, simply because that's how most compasses are written, and that's used in navigation, particularly ocean navigation. Is used almost exclusively with degrees, because latitude, longitude are all in degrees. But then we're going to have something, we're going to start working with our vectors here, because we're going to find something called the component form of a vector. So finally going to do a thing that's not just writing things down on this bottom one. So the component form of a vector is if we are given like array A, B, where we have an initial point at A and a terminal point at B. Our component form, meaning if we put it into its home formation where it was at that origin, when we put it into that piece, the word of it is escaping my brain. If we put it into its standard position, that was the word that was escaping my brain. Then what we do is we put it in our wedge notation is what this is called, because we've got these angled brackets. And what this is this is the change in the x's versus the change in the y's. So it's very similar to like slope. The little triangle, that's our delta. That means the change. So this is the difference in the x's. So x2 minus x1. And the change in the y's. y2 minus y1. And what that is that our initial point is the 1, and our terminal point is the 2. So point A is going to be our x1, y1, and our terminal is our x2, y2. And they will often be given to us in the form of ordered pairs. So we're going to find the component form from A of negative 2, 7 to B of 6, 1.
2 more days to survive.
So we want to find the difference in our x's. So if I was to write this, we could take our x of 6 minus the x over here, negative 2. What is 6 minus negative 2? And then do the same thing for the y's. We're going to find the change in our y's. So I'm going to take my 1 minus negative 7 is also 8. So the component form, we're going to put these angled brackets. We're going to have our 8, 8, close the bracket. It's weird. What this means is if I had a graph, so you don't have to plot this up, but if we had it, and I had a point at negative 2, negative 7, so we don't, over here, up to 6, 1, this vector. So this is the guy we were given, our initial side to terminal side. If I wanted to start at the origin, and I wanted this thing to get to its initial position, the terminal point would be, if I was better doing it, at 8, 8. So if I'm resetting this to be at its initial position, or its home spot, back to the origin, that standard position, its terminal point would be at 8, 8. To find the component form, no. Can it be facing other directions? Yes. It can face in any direction. I can have a vector that goes this way. I could have a vector that goes this way. I could have a vector that goes this way. I could have a vector in any direction. It's all about where our initial point is and our terminal point is.
So they're going to be like the same direction, the components are original?
Yes. They should always look like parallel lines, basically. Mm-hmm. Yeah, these are one of those things that it's really weird to wrap your brain around, so it's all a matter of finding where the sticking points are and rewording it for that. Okay? So it's all about finding that distance, finding the change in, figuring out how things are matching up. We're going to try that again, just to get used to it. So we're going to find the component form if we're given our initial point at 0, 8, and our terminal point at negative 9, negative 3. And I'm just going to get a... Mm-hmm. Yeah, I hear a lot of you guys looking at this and working through it, and I love that. Go for it. I'm just getting a little piece up here. So since, because we like the visual, I'm going to give us the visual. You don't have to put it in here, but I'm going to give it to us. So what this is telling us is that if I get my initial point at 0, 8, 1, 2, 3, 4, 5, 6, 7. Oh, I love that. I gave myself one spot, 2 feet. So 0, 8, and our terminal spot at -9, -3. 1, 2. You're right, that's 8, 0. I'm so good at these things. 5, 6, 7, 8, 9. 1, 2, 3. So there's our terminal point, 0, 8. 1, 2, 3, 4, 8. So this is what we're given. The vector that looks like this. That's the information we're given. And so we're trying to find our component form that from the home base bit. So we want to find the change in our x's and find the change in our y's. So the change in our x's, we're looking for how we went from -9, I don't know why I put a parenthesis there, to 0. So -9 minus 0, we want the difference between them. So the change in x is -9. The change in our y's we get from doing our -3 minus 8. We're always going to take our terminal side and subtract our initial side. So with the change in our y's is -11. So the component form of our vector, we're going to have our angle brackets. The change in x was our -9, and our change in the y's is our -11, angled bracket. Because if I was to move this down so it was at that initial position, that home position, we would be at our -9, 6, 7, 8, 9. To -9 minus 11, it would be like this. That puts the origin at home, the initial point at the origin, home base, and our terminal point is then at -9, -11. So the component form just resets it so that the initial point is the origin. Okay. So it's weird and kind of foreign, but the calculation part is not super duper difficult right there. One more page with writing. Okay. Last like really wordy page.
Wait, why does it have the angle bracket? Like, what can't they?
Because it's not just a point, that's our way of saying this is a vector, not a point.
It doesn't stop.
Yeah, because that means the direction is important and the distance, that magnitude is important. All right. So our last bit, and then we'll see why this was in the trig thing. We've got some new notations.
This is getting a little bit too complicated for my understanding.
So we have,
Too many symbols.
to be fair, most of them are symbols we've seen before. The little thing that looks like a little ray up here, that just means it's the vector. We can give it a name. V, usually. That is a V. The font is weird for math stuff. It's a V. And that's just when we have those angled brackets. So those origin-based vectors. That's when we can give it a name. It has to be in that home position where the initial point is on the origin. That's when we get these angled brackets, and that's when we get a vector that we can just name like this. And we just give it a name, A with an arrow at the top, B with an arrow on the top, V with an arrow on the top, whatever. You can use whatever letter we want. But the little arrow means we're talking about a vector. This double absolute value thing, which some people use a double, some use a single. I'm going to stick with the double because it makes it clear for us. It's finding the magnitude. That is the distance. How far did it go? So that's actually the distance formula. since we got our component form of our vector by finding the change in our x's and the change in our y's, it's just taking that part out of the distance formula, because now it's just the x value of our vector and the y value of our vector. So to find the length, how long our little arrow piece is, I'm going to go back for just a second. I'll bring it back to here. So looking at this guy, our magnitude is how long the piece is. So doing the distance formula to get from the initial point to the terminal side means we just have dropped these pieces out. We've already done that calculation. So that's why we can use just the square of the x value and square of the y value. Question, David, or stretching? Good. Cool, cool, cool. So if we want to find the direction, the angle, yes, dear?
What are those other formulas like beta?
That's where I'm just about to talk about. Okay? So if we want to find the direction, meaning I could find my heading, I could find my bearing. I want to know, again, I'm going to flip back. If I want to know this angle, this is the angle we're talking about. Okay? So to find the angle, we have a trig formula. We're going to have the inverse tangent of y over x, or based on where we have our domain of inverse tangent, we might need to have plus pi to get those coterminals based on what quadrant our vector's in. So we're going to have to pay attention to what quadrant we're in. Okay? So if we're in degrees, we add pi. If we are in radians, we add, or if we're in degrees, we add 180. If we're in radians, we add pi. So we might find things in radians, we might find things in degrees. So let's do one. Okay. Ready?
No.
I was going to say, I promise you're just overthinking it. I'll give you a second. Not to weep, but all right. So we're going to find our component, our magnitude, and our angle if we know our initial point is at 2,6 and our terminal point is at 7,11. We can get a Slurpee on our way. If you bring your own money. I'm not providing Slurpees. All right, so to get our component form, that's when we're finding our change. We want the change in our x's and the change in our y's. So the change in our x's, we take our b minus a. So we're going to have our 7 minus 2. So the change in our x's is start with b minus a. Every time. A is our initial point. The other way you can tell is if we look at this notation, A is on the side that doesn't have an arrow, so that's our initial point. B is on the side that does have the arrow, so that is the terminal point. So that little notation gives us a reminder on that. So our change in y's, that's not the pen I wanted. What is our change in y's? Yeah, it's 11 minus 6, so we also get a 5 here. Which means our component form, when I draw it in my angle brackets, is going to be what? 5, 5. What quadrant is that going to be in? Quadrant 1. Quadrant 1. So that means when we're trying to find our angle and stuff, we know that it's going to be in quadrant 1. So this is our component form. Just writing it down so we remember.
So for the x squared and y squared, we use the component form, or
For all the other calculations, we have to use the component form. So this is our vector, which I'm just going to call this vector A. This is the guy that we can use to calculate our magnitude and our angle. We cannot use the individual points. We can use the component form. You can call it V, you can call it A, you can just have it be the vector. Hang on a second. So let's look at our magnitude.
The square root of 2.
We're going to do the square root. We need our x squared plus our y squared.
Which would be 5.
So our
Root of 2, right?
magnitude, it's like a double line absolute value. Magnitude of A, we're going to have our square root of 5 squared plus 5 squared. So our magnitude of A,
It was a simplified radical.
either way, I'm not super petty about, because 5 squared gives us 25, 5 squared gives us 25, so we get square root of 50. Or I'm also okay if we put that in our simplified radical form, which is going to be 5 root 2.
I said that, but I think people root is like I get the term root.
That's fine.
No, I've been using it for the last 3 years.
That's okay. So that's our magnitude. And the symbol for our magnitude is that double absolute value.
You know what? I like that.
Then we're going to find our angle, our direction, theta.
I love chess.
And our formula for that is our arctangent of 5 over 5. Or I'm going to put the formula here, of y over x.
Just one,
Mm-hmm. So for this one, we're going to do our theta is arctangent of our 5 over 5. Or arctangent of 1. So what is our angle on this point? 45 degrees. Or pi over 4 if you're going radians. Because what this is saying, and I'm going to grab a graph real quick to put on the whiteboard.
That's a lot, right? It's intersecting at 45. It's moving that direction.
All right, I'm going to put it over here by the weak thing.
Was this the last question?
Yeah, I'm just going to throw it real quick.
Crazy.
All right, so if we have this and we graphed it,
That's a good signal. We actually got a different level in mathematics.
so our values that they gave us, so we had starting at the point 2, 6, 2, 6. Okay, cool. And terminal side at 711. I'm gonna be off the ground. 711's up here somewhere. So this is what the vector that we were given originally looks like.
Oh.
When we put it into its component form and scooched it down to be at our 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This being our terminal point. This is our component vector. This is our A.
And it's
And the
45
angle that they're
degree
telling us
angles.
is that this guy is 45 degrees.
Does it start from the east? Or does it matter?
Wait, so when will we have?
You're right, it's stretch from the north, gives us our heading. I'm gonna double check that real quick.
Well, she thought
So like when will we add 180? Like if it was like.
If we had something in quadrant 3, so if we had -5, find out the our terminal point, that's when we would need to look at our plus 180 to find our angle that gets us over to quadrant 3. Okay? So it's based off of those pieces.
it's pretty easy.
Okay, so it's not brutal. Alrighty?
I feel equations look too.
Okay, I was right the first time. Our angle is based off of the standard position of our angles back. Oh, gee, off of the x-axis. My instinct was right. I followed you, but I So it is off of our x-axis just like it is for unit circles. So this is our 45. This guy down here. So again, we have our 180 over here. So if we need quadrant 3, we'd add our 180. Okay. So it's based off of our x-axis values. All right, we're gonna work more with vectors. All of 8.3 involves vectors and 8.4. So, we're not doing book problems this time. Since this is also the homework that you will have over spring break.
Yay, homework or spring
I
break.
gave you guys, well, to be fair, we can do a good chunk of it. Number 3, you guys can do entirely. Number 1, you can do entirely right now. And we could get about half a 6. All right, so this is the homework for section 8.3. Instead of doing book problems, because it is really kind of weird.
I'm excited for spring break.
Am I excited? Yes.
I would
Very,
those are
very much. All right, so this is the homework for 8.3.
Sorry. I'm good.
Instead of doing book problems, I have extras. If you do, I have extras. Because I'm the same kind of way. This has been so long since I did vectors, I had to look and make sure I knew where the angles were coming from.